All right, so I got a few questions on just through email on some of the problems in chapter 2 in your book. So you can always email me problems. You can also ask them on the Talk to Me forum, and I'll respond to you as quickly as possible with a video. I feel like that's the best way to answer these questions. So in chapter 2, problem 15, what is one of them? So the question says acids from the health food store. So many important biochemicals are organic acids, such as pyruvic acid, which has a pKa of 2.5, and lactic acid, which has a pKa of 3.86. So the conjugate bases are pyruvate and lactate, respectively, of course. So the conjugate base is always, you just have 8, basically. So for each acid, determine which form, the acid or the conjugate base, predominates at pH 7.4. So let's go through that now. And this type of question, you could use the Henderson-Hasselbalch equation, but you really don't need to. It's something that you should be able to intuit with a little bit of practice. So for let's start with pyruvic acid. So pyruvic acid is OH. It's got a carboxylic acid group, COCH3. So this is obviously the protonated form. So this is the acid form. And so that's going to be interchangeable with, or, in a reversible reaction will be protonated and deprotonated. So this is the acid or protonated form of pyruvic acid. So the deprotonated form would be COO negative. So there's this COCH3. So the question is asking which predominates at pH 7.4. Well, the pKa is 2.5, which means that at the pH 2.5, this form and this form are going to be present in equal concentrations. So below pKa 2.5, this form is going to predominate, whereas above pKa 2.5, the deprotonated form is going to predominate. So if you have a lower pH, there's going to be more protons in the solution. So it's going to be definitely the protonated form. So you could use the Henderson-Hasselbalch equation for this, but you really don't need to because it's really important, actually, that you realize that above that pKa, so at pH 7.4, the deprotonated form is going to predominate. And this will actually, it's a really good check on problems that do require the Henderson-Hasselbalch equation. So let's also look at, so this one's pyruvate right here. So pyruvate, the conjugate base, also called A minus, and this is called HA here. Sorry, it's a little bit messy, but hopefully you can follow along and realize what I'm talking about. Okay, so lactic acid is very similar molecule, actually, and we'll go over this when we talk about metabolism. So the HA form, the acid, the protonated form of which is lactic acid, is going to have a very similar structure. So it's going to be COOH, and then it's going to be CHOH-CH3. So very, very similar. And so this is going to be reversible with the A minus form, the conjugate base, the deprotonated form. So you do need to understand what each of those terms mean. So A minus is conjugate base, deprotonated. HA is the acid, and that's the protonated form. And so that's going to be called, lactate. And so that's going to be COO negative because it's deprotonated, and then CHOH-CH3. And so this has a pKa that's just slightly above pyruvate or pyruvic acid. So this is 3.86. So at a pH way up at 7.4, again, this form is going to predominate. So you could use the Henderson-Hasselbalch equation for these types of problems, but you really don't need to. I do suggest that you look at this with like histidine. That's a really easy question to ask on the exam. The pKa of histidine is X, and at pH of Y is the protonated form or the deprotonated form, which one predominates. So take note of that, because that's a really good question to ask on an assignment or on an exam. Okay, the next question was that someone had an issue with was problem 17. So this one's called pH indicator. So a dye that is an acid, HA, and appears as different colors in its protonated and deprotonated forms, can be used as a pH indicator. So suppose that you have a 0.001 molar solution of a dye with a pKa of 7.2. So from the color, the concentration of the protonated form is found to be 0.0002 molar. So assume that the remainder of the dye is in the deprotonated form. So what is the pH of the solution? So for this one, what information do we have? So it's a 0.001 molar solution, and the dye has a pKa of 7.2. And we know that the concentration of HA, the acid, is 0.0002. So how do we solve this problem? Well, what else do we know actually? Well, we know if the concentration of the acid is 0.0002 and the concentration of the whole solution is 0.001 molar, sorry, this is molar, then we know that the concentration of the conjugate base is 0.001 molar minus 0.0002 molar, which equals 0.0008 molar. Okay, so that's all the information we already got. So now we can just plug that into the Henderson-Hasselbalch equation, which is, of course, pH equals pKa plus the log base 10 of the conjugate base over the acid. So we don't know the pH. That's what we want to know, but we do know the pKa. So that's 7.2 plus the log base 10 of the conjugate base concentration, which is 0.0008 molar, over the acid concentration, which is 0.0002 molar. So you can plug that into your calculator. If you have any issues with that, let me know. I can make another video. So pH equals the pKa, which is 7.2, plus the log base 10 of 4, because 0.008 divided by over 0.0002 is 4. So that actually turns out to be 0.6. So the pH equals 7.2 plus 0.6. So if you do that math, the pH equals 7.8. So that's the answer to that question. So it really is just plug and play. So this is my least favorite part of this course, but it is an important part of biochemistry to understand acids and bases and buffers. So that's why we take one lecture and go over it. Okay, so problem number 18 was the next one that was an issue. So what's the ratio? So an acid with, and just get used to writing that. So acid with a pKa of 8.0 is present in the solution with a pH of 6. So what is the ratio of the protonated HA to the deprotonated form of the acid? So what information do we know? We know the pKa equals 8 and the pH equals 6. So we can plug this into the Henderson-Hasselbalch equation. pH equals pKa plus log of the conjugate base over the acid. And so we know that the pH is 6. So that equals 8 plus log, let's write the base 10, of the conjugate base over the acid. So let's just do algebra. Subtract 8 from either side. So -2 equals the log base 10 of the conjugate base for the deprotonated form over the protonated form. So now we can take the anti-log. So I just do this thing. So 10 to the -2 equals the concentration of A minus over HA. So that ratio of deprotonated to protonated form equals 0.01. So that equals the deprotonated form over the acid form. But it's asking you for the ratio of the protonated to the deprotonated form. So that's actually HA over A minus. I'm not going to do this to you on the exam. The book's just trying to push you a little bit. So really, you can just turn that negative into a positive. So it's 10 to the power of 2, which equals 100. So the deprotonated form over the protonated form equals 0.01. So that's 10 to the -2. And then if you switch those around, it's 10 to the 2. So that's why the answer is 100. So hopefully that's clear to everybody, explaining that. But they're trying to trip you up a little bit. Okay, this last one I don't like. I should take it off. I forgot to take it off because it goes a little further than I'm really asking you to. It's more of a general chemistry question, but I'll go through the part that you do need to know, and then I'll go through the part that is a bit beyond what you need to know very quickly. So this problem says another ratio. So calculate the concentration of acetic acid, which we know is the protonated acid form, and acetate ion, which is the deprotonated form, in a 0.2 molar acetate buffer at pH 5. And the pKa of acetic acid is 4.76. So how do we do this one? Of course, we're going to use the Henderson-Hasselbalch equation. pH equals pKa plus the log base 10 of acetate over acetic acid. And so we know the pH, so that's 5 equals 4.76, which is the pKa, plus the log base 10 of acetate over acetic acid. So algebraically, we subtract 4.76 from each side. That gives you 0.24 equals the log base 10 of acetate over acetic acid. And you find the anti-log right there. So that would be 10 to the 0.24 equals the ratio of acetate over acetic acid. And then if you just plug that in your calculator, 10 to the power of 0.24 is 1.74. So that's the ratio of acetate over acetic acid. This is as far as you need to go in this course. I'm not interested in messing with buffer, making buffers or anything like that. If you take a lab, you'll sort of learn that stuff, but it's not super important. And that's sort of where this question is going and what is tripping people up. But I'll go through it right now really quickly just so that you have that information. So we know that the conjugate base concentration equals 1.74 times the acid concentration, because there's it's basically 1.74 over 1. So if you multiply the acid by 1.74, that's going to be the conjugate base concentration. We also know that the buffer is a 0.2 molar buffer. So what that means is the conjugate base plus the acid concentration is going to equal 0.2 molar. What we also know, just if we rearrange that algebraically, is that the conjugate base concentration is going to equal 0.2 molar minus the acid concentration. So what we can do is we can plug this part into that part of the equation. So that gives us 0.2 molar minus HA, because we're replacing this basically equals the concentrate. We know that that equals the concentration of the conjugate base equals 1.74 times HA. So we can rearrange that a bit further algebraically and do 0.2 molar equals 1.74 times HA. And then we're basically adding this to either side, plus HA. So plus 1 HA, or the acid concentration. So that gives us 0.2 equals 2.74 because we're adding 1.74 plus 1 times HA. So now we can take 2.74 from either side. And what that turns out is that the acid concentration is going to be 0.072 molar. So the acetic acid concentration in the solution is going to be 0.072 molar. But we also want to find the conjugate base concentration. So A minus plus, and this is basically, we're plugging this, we're going back to this equation right here. So the conjugate base concentration plus 0.072 molar, which is the acid concentration that we just found out, is going to equal 0.2 molar. So if we subtract 0.072 from either side, we find out that the conjugate base, or the acetate concentration, is going to equal 0.128. Again, that second part of the equation, that is not going to be on any exam that I'm going to give you. This part definitely will. You do need to know how to use the Henderson-Hasselbalch equation to figure out the ratio of the conjugate base to the acid, but I'm not going to mess with molarity. I'm not going to say, oh, you have a buffer solution of 0.2 molar or anything like that in any of the questions on the assignments for the exam. And really, we're going to be done with math for the most part in this whole course after this section. So thank you very much to the student who asked that question. And if anybody else has any sort of questions like this, I'm very happy to make these videos to explain them. So thank you very much for the question, and let me know if you have any more questions.